If a turntable takes 2 seconds to go from rest to its final turn rate, making exactly 3/4 of a full turn in the process, what was the turntable's angular acceleration alpha, assuming it was constant? So basically we're saying the question is alpha is equal to what, right? And maybe we could say, well, let's go to the definition of alpha, which involves the change in angular velocity over a change in time. And we are given, right, we are given a delta t is equal to 2 seconds. But let's see, we're not given anything about angular velocity. So, right, so if I wanted to say like delta omega over delta t, that seems like it wouldn't work. What information are we given other than this? Well, we're told that it starts from rest. Well, so I guess we could say, right, that omega naught is equal to 0, but we're not told like what final angular velocity it gets to. So again, that's going to be problematic if I want to use that delta omega over delta t. What other information could there possibly be in this question? Well, it does say exactly 3/4 of a full turn. So what does that mean, right? So we're talking about 3/4 of a turn. Written poorly here. Let me fix that 3. All right. More clear. 3/4 of a turn, right? I think I'm nitpicking on this here. I think that suggests, if we think about it in terms of angles, right? Like a full turn is 2 pi. And let me see, if I remember my unit circle, right, there's like the quadrantal angles are like pi over 2, pi, and then 3 pi over 2, and then 2 pi, right? But 3 pi over 2 really represents 3/4 of a full turn. So maybe I could write that as delta theta is equal to 3 pi over 2. And now I'm looking at this and I'm recognizing like, well, the omega naught is equal to 0. There was another formula that was analogous to the basic like distance as a function of time and acceleration formula that we started with in kinematics, but for rotation, right, it was delta theta is equal to 1/2 alpha times t squared. So maybe if I go up here and I say, you know what, I thought that it was appropriate to label this 2 seconds as a delta t, but maybe if I just call it a t, because that's the way I wrote this formula. And this is one of these things, is like, you know, is it a t, is it a delta t? Usually when you do kinematics, both linearly and rotationally, t kind of both represents the time that you're maybe evaluating at, like what is the position as a function of time. But you could also say it represents a time interval, which notation-wise, a time interval might be better represented with a delta. But it's a little slippery, really. Like, do you use delta or not use delta? So getting rid of that might seem like cheating, but it's more just like, you know what, I want to get a neat fit for the formula I'm going to use, right? And recognizing that alpha is the question, I think I can do a little bit of algebra here. Let me rewrite this. I'm gonna rewrite it with things on the opposite side so that I can more transparently see the algebra here. Because if I multiply by 2 both sides, I think I'm showing more steps than I sometimes do just because there's plenty of space here, so why not, right? And then maybe if I divide by t squared on both sides, I would get alpha is equal to 2 delta theta over t squared, which would be equal to 2. And I'm just going to put in here that 3 pi over 2. And then for t squared, I'd put in that 2 seconds and square that. And my calculator can handle all that if I put it in there. And maybe, you know, this is maybe another good example where if you have a calculator, want to pause the video and see if you can get the same result as I do, I would encourage doing that, because there's places to make mistakes and it's a good skill to keep practicing. Since we do it a lot in this class, is like evaluating things with some kind of calculating device. I get like 2.356194449, and I think I'd like to round that off to 2.36. What about the units? This would be like radians per second squared is what we expect. There is a second squared down there, but as I've discussed, I usually prefer not to use any kind of written form of radians, like an R or whatever you would use. I've seen some different examples in different books, but most physicists, recognizing it doesn't contain any dimensions, don't bother to write it. So this is the appropriate way to express 2.36 radians per second squared, and that checks out with what the slide says the answer should be.